Going to look at the integration of a composition of functions. Now, if this is the first time you are seeing my face, hi, my name is Dr. Marissa May. I'm on a mission to help students feel confident in their math classes. So I'm glad that you've joined me. Let's take a look here. We're going to really we're going to build up this concept of the integration of a composition of functions. But I want us to start with the function and take the derivative approach to it. So if I take the derivative of f of x equals sine of x, I want you to think chain rule. So the derivative of sine would be cosine of 3x. And then we have to multiply by the derivative of 3x. Well, the derivative of 3x would be 3. So that would give me 3 cosine of 3x. Now, if I take the integral of this, if I take the integral of 3 cosine of 3x dx, I should get back sine of 3x, which makes sense with the cosine part, but it doesn't make sense with the 3 in front. I should get back sine of 3x, but that 3's in wrong. It looks like it's kind of out of place, but it's necessary to be there. Okay, let's look at the next one then. F of x equals e to the cosine of x. Okay, so again, chain rule. The derivative of e is e to the cosine times the derivative of cosine. The derivative of cosine is negative sine. So f prime of x here would be negative sine of x e to the cosine of x. Now take the antiderivative of the derivative. We should get back the function, right? And I forgot on these my plus c, so forgive me, I'm adding those in there. Okay, so very important when we have this nested function, we have this composition of functions, that we have the derivative of the inner function sitting there. That's important. Okay, let's look then at ln of x squared plus 3. Well, the derivative of the ln would be 1 over x squared plus 3 times the derivative of x squared plus 3, so times 2x. So we get 2x over x squared plus 3. So if we take the integral of the 2x over x squared plus 3 dx, we should get back the function. And again, notice that 2x in the numerator, that is the derivative of the inner function, it's sitting there on top. Let's take the derivative here. First, let's rewrite it. So I can rewrite it as x squared plus 3 to the 1/2. So the derivative here is 1/2 x squared plus 3 to the negative 1/2, and then times the 2x, which would be the derivative of the inside, the derivative of x squared plus 3. So if I clean that up, I've got the 2x, or sorry, the 2 times a half, that gives me 1. So I've got the x on top. And on the bottom, I've got the x squared plus 3 to the 1/2. Okay, so if we take the antiderivative of the x, the derivative here, the x over x squared plus 3 to the 1/2 dx, we should get the function back. All right, so what does that mean? Well, we need to recognize some things. First of all, if we take the derivative of a composite function, we have to take the derivative of the outside of the function times the derivative of the inside function. Consequently, if we have that in our integral, then we should get back a composite function plus a constant of integration there. Okay, let's take a look at putting this a little bit more together. Okay. Okay, so let's look at a pattern here. Remember, if we're going to take the antiderivative of a function that has an inside function, I've got to look for that inside function to have a derivative sitting there. Okay, meaning if I'm going to take the antiderivative of cosine of 3x, I've got to have the derivative of 3x sitting in the integral as well. In this case, I do. So I would get sine of 3x here plus c. Okay, look at the second one. I'm going to rewrite this with a uh, exponent of 1/3. Okay, so your inner function here is x squared plus 5. The derivative of x squared plus 5 is 2x. It's sitting right there. So I'm going to go ahead and integrate this x squared plus 5 by increasing the power, x squared plus 5 to the 4/3 over 4/3 plus c. Okay, now go ahead and clean it up by flipping the fraction and multiplying. Okay, look at this as your inner function is 2x plus 3. The derivative of that would be the 2 sitting here. So we're going to go ahead and integrate sine of 2x plus 3, which would be negative cosine of 2x plus 3 plus c. Okay, now, okay, think of this as your inner function is x squared plus 2x. The derivative would be 2x plus 2, which is sitting on top. So I want you to, we're going to integrate 1 over, because you might want to think of this as 2x plus 2 times 1 over x squared plus 2x. So we'll go ahead and integrate the 1 over x squared plus 2x, which would be the ln of x squared plus 2x plus c. Okay. Now look at this one. I've got my inner function is 3x plus 2. The derivative of that is 3, but there's no 3 sitting out here. So here's what I want you to think. I'm going to put a 3 in there. And you may be thinking, Dr. May, you can't do that. Well, I can if I also put a 1/3 out here. See, because 3 times a third is 1, and I balance it. Okay, now I can take the antiderivative of the cosine of 3x as long as I put the 1/3 in front of it. So the antiderivative of cosine of 3x is sine of 3x plus 2 plus c. So if you don't have that derivative sitting in front, you can multiply by a number, not a variable. Okay, let's take a look at this one. I'm going to rewrite it. 3x times x squared plus 2 to the 1/2 dx. Okay, the inner function is x squared plus 2. Derivative is 2x. So I have the x there, but I don't have the 2. So I'm going to need to put a 2 there. And as long as I put a 1/2 in front, we should be okay. Now, but the question is, what do I do about the 3? I got to get it out of the way. So I'm going to pull it in front with the 1/2. Now I have my 3/2 sitting in front. We have our derivative 2x sitting there. So we're good to integrate x squared plus 2. So that's going to be 3/2 times x squared plus 2 to the 3/2 over 3/2 plus c. Now check out your denominator. 2 times 3/2 is 3. 3 divided by 3 is 1. So this ends up being x squared plus 2 to the 3/2 plus c. Okay, Now we have 5e to the 3x. Okay, the inside function is 3x. The derivative is 3. I don't have a 3 sitting out here, but I can make one. So I've got a 3 now. And I can do that as long as I put a 1/3 in front. Okay, the 5 I'm going to pull out with the 1/3. Now I've got an inner function with its derivative sitting right there. So I'm going to integrate e to the 3x, and that would be e to the 3x. Okay, last one of this type. Let me rewrite. So I want to kind of make it clear what we're looking at. So I've got 3x times 2x squared plus 3 to the negative 1/2 dx. So my inside function is 2x squared plus 3. The derivative would be 4x. I've got the x, but I don't have the 4. So I'm going to put the 4 there as long as I put a 1/4 in front. Okay. So the 3, I'm going to pull it out in front with the 1/4 just to kind of get it out of the way. That way I've got my inner function is 2x squared plus 3, and its derivative 4x is sitting there. Okay, now I can integrate the 2x squared plus 3. So I've got this 3/4 in front. The antiderivative, let's see, I would be 2x squared plus 3 to the 1/2 all over 1/2 plus c. Now look at your denominators. 4 times a half is 2. So you end up with this fraction 3/2 in front, and you've got 2x squared plus 3 to the 1/2 plus c as our final antiderivative. Okay, now all of that leads us into a technique called U-substitution. Okay, so in the example that we had before, we had the ability to integrate because we had the derivative of that inner function sitting there. So sometimes the derivative doesn't exist or it's not really available by just multiplying by a number. So what do we do then? Okay. In this example, I want you to see that the inner function is actually the 2x minus 1. So the derivative of that would be 2. Is this 2 in the integral? No. Is it attainable by multiplying the integrand by a constant? We could do that in this case, yes. So let's let u. So the problem in this one is that that x is sitting there. So you see that the derivative is only a 2, but we don't have the x. We would have to do something with that. Okay, so let's let u be the inner function, 2x minus 1. We want to find du and solve for dx. Okay, so the derivative of du dx would be 2. The derivative of 2x minus 1 is 2. I'm going to multiply both sides by dx. So I've got du equals 2 times dx. Then I want to solve for dx. So I'm going to divide both sides by 2. That gives me dx equals du over 2. Okay, now find an expression for x in terms of u. So take this guy and solve for x. So I'm going to add 1, and I'm going to divide by 2. Or you might want to think it as 1/2 times u plus 1. Okay, now we take our integrand and rewrite it in terms of u. So we're going to take x times 2x minus 1 cubed, and I'm going to substitute. In place of x, I'm putting the 1/2 u plus 1. In place of the 2x minus 1, I'm putting a u. Now, if I do a little bit of manipulating, I can integrate here. So I'm going to pull the 1/2 in front, and I'm going to distribute the u cubed. So u cubed times u to the 4th. U cubed times 1, u to the u cubed. Now you can integrate because these are just being added together. So let's do that. U to the 4th would be u to the 5th over 5. And then I've got to distribute the half. And then u to the 3rd would be u to the 4th over 4, and then plus c. Now, all we have to do then is to make this 1/10 u to the 5th plus 1/8 u to the 4th plus c. Now, the problem here is that our integral did not start out in terms of u. It started out in terms of x. Therefore, we've got to go back to x. So let's remember what u was, 2x minus 1, and let's put that in there. 2x minus 1 to the 5th plus 1/8 2x minus 1 to the 4th and plus c. Okay, let's do one more like this so that we get a really good feel. This time we're going to do the integral of 2x plus 1 over the square root of x plus 4. And just a hint, a lot of times we could use 2x plus 1 as our our inner function, but more importantly, notice that the x plus 4 is underneath the square root. That's where I want to start with my inner function. So I'm going to let u be x plus 4. So du dx is going to be 1. So du equals dx. That was pretty simple. Okay. Now we find an expression for x in terms of u. So take your u and solve for x. So I'm going to subtract 4 from both sides. Now let's take our integral and convert to u's. Okay. For simplicity's sake, I'm going to bring that x plus 4 to the negative 1/2 to the top so that it looks something like that. Okay. I'm going to make the substitutions. So I've got 2 times x, which is u minus 4, plus 1. And then x plus 4 is u to the negative 1/2, du. Okay, let's distribute that 2. So I've got 2u minus 8 plus 1, and that would be 2u minus 7. And then let's distribute the u to the negative 1/2. Now, friends, remember, I'm doing a lot of simplifying to make the calculus easier, okay? So that gives me 2u to the 1/2 minus 7u to the negative 1/2. Now let's integrate. We're going to increase the power by 1. So that becomes u to the 3/2 over 3/2 minus 7u to the 1/2 over 1/2 plus c. Now flip and multiply gives me 4/3 u to the 3/2 minus 14 u to the 1/2. And our last step, friends, then is to make sure we go back to x. So I've got 4/3 x plus 4 to the 3/2 minus 14 x plus 4 to the 1/2 plus c. All right, one more example here. I like this one because it has bounds with it. And we definitely need to work through one with bounds. So let's choose our inner function. Looks like I would let that be 2x plus 1. So I'm going to let u equal 2x plus 1. Then I'm going to solve for du. So du dx is 2. So du equals 2 dx, and dx is 1/2 du. Okay. Step 3, solve for in terms of x. So you're going to take your u and we're going to solve for x. I'm going to subtract 1. Then I'm going to divide by 2, but I'm probably going to write it as multiplying by 1/2. Okay, now make our substitutions. I will deal with the bounds here in just a minute, okay? So x becomes 1/2 u minus 1, and square root of 2x plus 1 becomes u to the 1/2. And then in place of dx, we put 1/2 du. Now, I left the bounds off because I want you to think of these as x's bounds. If x is 0, 2 times 0 is 0, plus 1, u is 1. If x is 4, 2 times 4 is 8, plus 1 is 9. Now you have u's bounds. So here's the deal. By changing the bounds to u's bounds, I do not have to go back to x. Okay? Very important. Let's clean it up and take the integral then. 1/2 times 1/2 is 1/4. U minus 1 times u to the 1/2. So we're going to distribute the u to the 1/2. Becomes u to the 3/2 minus u to the 1/2. And now take the antiderivative. Okay, so that becomes u to the 5/2 over 5/2 minus, don't forget to distribute your 1/4. The antiderivative of u to the 1/2 would be u to the 3/2 over 3/2. And then we go in with our bounds from 1 to 9. Okay, look at your denominator. That becomes 10 in the denominator. So you have 1/10 u to the 5/2 minus 1/6 u to the 3/2. Again, going from 1 to 9. Now, friends, when you deal with the rational exponents, I want you to do the square roots first. Here's what I mean by that. When I do this, I'm going to do 1/10 square root of u to the 5th. I'm going to do that first, square root of u, and then do it to the 5th power. It's going to be a lot easier, especially if you're calculating by hand. Okay, put in your 9. Okay, so I've got 1/5, or sorry, 1/10. Square root of 9 is 3. 3 to the 5th is 243. Okay, minus 1/6. Square root of 9 is 3. 3 cubed is 27. Okay, now minus, and then you've got to distribute. So you've got another parentheses there. Put in the 1. 1/10 minus 1/6. Okay, so just a little bit of cleanup here. That's going to give you 24.3 minus 1/6 times 27 is going to give you 9/2, which is 4.5. Minus, and then you've got 1/10, 0.1, and then 1/6. That's just going to be a decimal that doesn't terminate, so we'll leave that. Let's see, this gives me 19.8. And then I've got minus zero point 0.1 and then plus 1/6. So that gives me 19.9 and then plus 0.16 repeating. Let's see, that's going to give me really close to 20.1 there. Okay. But you realize when I changed the bounds to u's bounds, I did not have to go back to x's bounds. So I hope that helps with this topic. Keep practicing. The only way to get good at U-substitutions is to practice with them. And so practice, practice makes progress. So let me know if I can help in the comments below. Thanks for watching, and I hope you have a good day. Bye-bye.